Welcome to the Math S1. I am sure you are here to understand more about the topic that we'll discuss, especially to those people who did not pay attention to their teacher. Kidding aside, you're lucky because this is the perfect video for you to easily comprehend the topic, related rates, and optimization. Before we proceed to the video, don't forget to like and share the video for the updates. Have fun because Math is fun.
I'm Sebastian, and for today's video, I'm here to teach you on how to solve a problem about related rates. But before we start solving, let me introduce to you what is related rates so that you understand more about it. In differential calculus, related rates problems involve finding a rate at which a quantity changes by relating the quantity to other quantities, whose rate of change are known. The rate of change is usually with respect to time. Let's now proceed with the example. Here's the problem. A right cylindrical tank is filled with water. The tank stands upright with a radius of 7 feet. How fast does the height of the water in the top tank drop when the water is being drained at 35 feet cubed per second? Here, let's identify what are the givens. We are given with the values of radius with 7 feet and negative 35 feet per second. So, do you think why in here it is negative 35? Because the negative rate is due to the fact that it decreases when the water is being drained from the tank. With this given, it is now clear that we are looking for the change of height over change of time, or dH over dt. The needed formula for the volume of the right cylinder is V, or volume, is equals to pi r squared h, or height. Formula contains a radius, but in this problem, the radius is constant, so it's not a variable. And then, if it's not a variable, then, with respect to r, we need to differentiate both sides of the equation to obtain dV over dt equals to pi r squared dH over dt. Then, we can now substitute the value, and we're going to have dV over dt is equals to pi 7 squared dH over dt. By substituting dV over dt, we obtain pi 7 squared dH over dt equals to negative 35. Next, we just need to continue solving for the equation, and we will end up with 49 pi dH over dt is equals to negative 35. And solve for the dH over dt, we must divide both sides by 49 pi. So, we'll end up with negative 35 pi over 49 pi, and we need to simplify it for the final answer. So the answer is negative 5 over 7 pi. Finally, we can conclude that the water's height is decreasing at a rate of negative 7 feet per second.
My name is John, and today we're learning about related rates in calculus. Today's example will be a word problem. So I read it to you guys. So air is being pumped into a spherical balloon at a rate of 4 centimeters cubed per minute. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. First off, identify the given numbers, of course. So the rate of change of the volume is dV over dt. The value is 4 centimeters cubed per minute. Then the diameter is 20, given from the problem. Then the radius will be halving the diameter, which is 10 centimeters. And we are looking for the rate of change of the radius, which is dr over dt. We'll find that using the derivative of the equation of the volume of the sphere. The volume of the sphere is 4/3 pi r cubed. The derivative of it is 4/3 pi 3r squared dr over dt. Now we'll simplify that value, or we'll simplify that equation by cancelling the 3's from 4/3 and the 3r squared. So eventually it will become 4 pi r squared dr over dt. Then we'll plug in the values for dv over dt and the radius. So the equation will be this: 4 is equals to 4 pi 10 squared dr over dt, or simplify it, 4 is equals to 400 pi dr over dt. Now we isolate dr over dt to find its value. So we transpose 400 pi to the other side. 4 over 400 pi is equals to dr over dt. Now we'll simplify that fraction to get the final answer. 1 over 100 pi is equals to dr over dt. Now that's your final answer. That's the rate of change of the radius.
Optimization is the process of finding maximum and minimum values given constraints using calculus. In the optimization problems, we are looking for the largest value or the smallest value that the function can take. Hi, I'm Ashley Alvarez, and I'll teach you how to solve an optimization situation. A rich man plans to fence out his backyard. Having 5,600 meters of fences, he wants to add borders in a rectangular form, not including the back part of his house. What are the dimensions of the field that has the largest area? To solve this equation, we have 5 steps. Step 1 is to draw what is said to this equation. So we have here an aerial view of a house and a rectangular shaped backyard. Step 2 is to create objective and constraint equations. It is seen that we wrote the formula of the perimeter and area of a rectangle. Analyzing on what we wrote for our step 1, we are finding for the measurements the sides of the rectangle. It is said in the problem that the back part of the rich man's house is not included. From 2x plus 2y is equals to 5,600, we reduce one side of the rectangle, and having our last formula, x plus 2y, is equals to 5,600. Step 3 is to make our self-constraints into our objective equation. From x plus 2y is equals to 5,600, we transpose 2y to the right side in order to find the value of our y. We need to multiply the equation by y to have our step 4. After multiplying y in 5,600 minus 2y, step 4 is to get its derivative. X is equals to 5,600 minus 4y. 2 times 1,400 is equals to 2,800. X plus 2,800 is equals to 5,600. We now have the chance to find the value of x by transposing the numbers to the other side. From x plus 2,800 is equals to 5,600, x is equals to 5,600 minus 2,800, having a difference of 2,800. Our y have a value of 1,400 meters and x for 2,800 meters. Therefore, the largest dimension of the rich man's backyard fences measures 2,800 meters by 1,400 meters.
Hello guys, I am Anna and this is the second example in optimization. The word problem is, a rectangular garden is to be built beside the wall of a house. 3 sides of the garden will be built using wood materials. With 80 feet of fencing, what is the maximum area of the garden and its dimensions? Step 1. Visualize and draw the problem, and we have a top view of the house in a rectangular garden. Step 2 is to create object and constraint equations. We can see that the formula perimeter and area of rectangle is 2x plus 2y is equal to 80. And since one side of the garden wall is the wall of the house, we reduce the side of the rectangle, making our formula 2y plus x is equal to 80. Step 3 is now to make the subconstraints into an objective equation. With the equation x plus 2y is equal to 80, we transpose x to the right and we get 2y is equal to 80 minus x. And we divide the equation by 2 and we get y is equal to 80 minus x over 2. Step 4 is getting the derivative of y is equal to 80 minus x over 2. We now have 0 is equal to 80 minus x over 2, and now we transpose x to the left and we are left with x is equal to 80 over 2. And now we know that x is equal to 40. Going back to our main equation, which is x plus 2y is equal to 80, we now substitute x to 40. And for our step 5, we now have 40 plus 2y is equal to 80, and we then transpose 40 to the right, which gives us 2y is equal to 80 minus 40, which is 2y is equal to 40, and divide both sides by 2, and now we get y is equal to 20. Our x has a value of 40, and our y has a value of 20. Therefore, the measurement of the garden walls is 80 times 40 feet. Thank you guys for listening, and I hope that you'll get a 100% grade on your basic math quiz topic related weights and optimization. Don't forget to like, share, and click the notification buttons, and please subscribe to our YouTube channel for the next video. Bye!